vanadium, zinc. Do something! So I thought this demo was going to be a quick and easy one to do, but it's been a ride. I think everybody who's been teaching after a few years has probably had some experience with the reduction of ammonium metavanadate 5 with zinc. It's such a ubiquitous reaction, but because of this, everybody has their own way of getting it done. And the last time I tried it, like here, it was slow. But that's fine. I left it running in the background on little plinth while we smashed through a load of practice, E-cell and spontaneity predictions. There are so many different ways of doing this reaction, and almost none of them actually tell you how long it might realistically take. There are going to be some school-specific things as well that could make your life more difficult. Getting the reaction to run fast will often come at the cost of clarity of color as the solution gets filled up with tiny bubbles or fragments of powder. So I thought that the best good that I could do for you would be to see if I could try out some different methods, get a sense for how long they take, and find out if it would be possible to accelerate this reduction so that you could reasonably run it as a demonstration. What follows is the result of literally a tear-inducing number of hours in the lab, but I'm really grateful for the support of all of the community out there on social media who've provided some fantastic ideas and helped me to move this forwards. I don't know how long this video is about to be by the time I do the edit, so if you want to cut past all of the preamble and just get to the meat, I'll probably leave a time code somewhere around here, and you can kind of skip to that from when I'm actually going to start doing the reaction. But there's going to be a lot of stuff along the way, and I would recommend you stick around, because I think it's important to understand what works, what doesn't, and what potential fixes there are when things do go wrong for you. There's some mad logic that I've had to go through that's going to help me to arrive at the slightly bizarre choice of equipment that we've gone for at the end, but I promise that by the time we get there, it will all make sense. So, where to begin? If you're a Eclipse member, you'll start by checking out the recipe book for producing a solution of ammonium metavanadate 5. This is a 0.1 mole per decimeter cubed solution in sulfuric acid, and it's the one that you're going to find most commonly in other literature as well. Do note the safety protocols in position here. Ammonium metavanadate powder is highly toxic, fatal by inhalation, so measuring carefully using splash-proof goggles, working in a fume cupboard with a lowered sash and the extraction off. This is important stuff to get right. The nice thing about this method is how easy it is to dissolve the metavanadate 5. You're making it up first in 2 mole per decimeter cubed solution of sodium hydroxide and then acidifying afterwards with sulfuric acid. You'll get these lovely color effects along the way. Note the pH dependence as well of the colors. There's more going on here than just dilution, and that's going to become crucial for us later on. Jim Clark's Chem Guide is a great place to drop in for some discussion on the exact species that we're seeing in solution. The zinc granules on the left are untreated as I found them in the cupboard, and it's just painful to watch. Clearly, the surface has become heavily passivated, but it can be rejuvenated, as you can see on the right, with a little rinse in some dilute copper sulfate solution. Here you can see on the right-hand side, with my sort of activated zinc, we are well off the starting blocks already. This reaction that you're seeing here is running at 30 times speed, and we're moving already from the yellow vanadium 5 to blue vanadium 4, and of course a mixture of the two of them along the way will appear green. We'll check back in with this reaction later on, but by the time I got this far, I'd also realized for demo purposes you may not need solutions quite as concentrated as 0.1 molar. The vanadium 3 is actually quite dark in color, and for a slightly larger scale reaction for in front of a class, you might find more dilute solutions give you better colors. Either way, with this setup, you're still going to be looking at a minimum of 50 minutes to get your reaction close to vanadium 2. It's not ideal for a typical lesson unless you have extended blocks of time to use. So how to speed things up? Well, basic understanding of kinetics tells us maybe we increase surface area by adding some powder, increase the temperature, or add a catalyst. And we had a bit of a clue to this in the last clip there. Cleeps suggests adding a few drops of copper sulfate into the solution for the latter of these, catalyzing. But I found sometimes that when you do this, you can get some discoloration from copper, and a deep frustration of mine with this reaction is the cloudiness associated with fine bubbles being produced off the zinc. There is a way to rejuvenate the old zinc granules. As I mentioned before, a quick rinse in some dilute copper sulfate solution will create a significantly more active surface to get your reaction going, and this removes any problem with copper discoloration, but bubbles can often still stop us seeing the reaction at its best. This might not bother you so much, but these vanadium colours are beautiful and we want to be able to enjoy them. There's a real subtlety to the vanadium 2,3 mixture which gets totally lost in a cloudy solution. Of course, bubbles tend to rise, so I wondered if the loop of glass tubing that many schools will have on hand for demonstrating convection might come in handy here. I could create an elevated platform for the zinc, and the vanadate solution could just kind of move past it. My first trial was with the zinc up top, using a candle to initiate convection on the bottom corner and drive the solution past, as well as gently warming. Still took an hour. And it did need at the end some encouragement from zinc powder to get over the finish line significantly into the vanadium 2 area. Clearly, powder is helpful, but how to stop it making a bubbly mess and floating around in bits everywhere? So then I thought I might be able to use a tea bag lowered into the solution containing some zinc powder. Let's give it a try. So I've got some zinc powder, I've got my spatula, and if Mark's still out there, yes, these are still your pots we can spot here. And if I just get a little bit of zinc, pop onto the side here, and I've cut like a little hole in the top. That's beautiful. Straight through. So my next thoughts after this were, maybe I could just kind of put the zinc inside some toilet roll, and the toilet roll would hold the powder in the bag long enough for a reaction to take place, but without allowing the zinc to slip through the net. It wasn't great. So I went back to my supercharged zinc granules. While the reaction was still not going fast enough for my liking, I wondered maybe if an oblong-shaped vessel, while I'm still trying to get it going faster, might provide an opportunity for us to view through different path lengths, ensuring that each colour gets its moments to shine. So after rummaging around like the whole department, in biology, I found one of these, and to my chemist friends who are like, what the hell is this? Apparently it's a cell culture flask, and it's actually really nice for running this reaction in. Let's give it a try. This is in a 0.05 mol per decimeter cubed solution now, following the Cleeps method, but at half the concentration of the vanadate. My granules in a tea bag are now producing some beautiful colors, and by viewing from different angles you can actually enjoy the various hues along the way. But speed is still a problem. Earlier on, we saw a trial that I ran using a casing from strips of indicator paper, a bit like this, and I was thinking along multiple lines here at the same time. And the clarity of the color that you get by sort of passing a light through this, compared to a test tube with all of its potential specular highlights and reflections, it's day and night. So With this small scale, the dimensions also provide benefits for keeping the cloudiness of powder additions to a minimum. Now, by carefully adding powder onto one side and occasionally brushing it across, I had a reaction running in about 20 minutes. And that maintains some really nice color clarity throughout. And at the scale of an indicator strip box, you can see this from some distance. For smaller classes, this may already be a good solution. Although I would recommend not using a visualizer, I often noted that the raw camera footage seemed to make vanadium 3 look a lot bluer looking than it actually looked in real life. So if you're projecting this onto a screen, it probably isn't going to look great. So it could work for a practical though, and this produces much nicer colors than just dumping powder into a tube of the solution and getting a cloudy mess. Speaking of practicals, do stick around at the end. Obviously, we have some microscale tips from Bob Worley, who's come up with his own method for doing this reaction as a practical as well. So, to recap, we now have an oblong vessel. We're using a tea bag to elevate the zinc, making sure that the bubbles travel up away from the solution underneath and keep that nice color clarity. But we still need this reaction to go faster for a reasonable demonstration that allows for discussion afterwards within the parameters of a typical lesson. This is where I put the call out on social media, and I was not disappointed with the fantastic help that came in reply. One really important piece of advice that I got back from Michael Ryan, he suggested that he'd also been using tea bags for some time with this experiment, and it got me thinking that actually maybe these kind of loose leaf style tea bags that I just happened to find in the cupboard when I was trying this out weren't the best option. They might have different properties from these kind of like string tag wrapped up cylinder with a staple on top type tea bags. So I thought I would give that a go. I got straight stuck back in with one of those, and I 100% did not regret it. While some powder still does go through, the tea bag is able to hold on to the majority of the zinc powder that we have in stock, at least here. I load in a couple of spatulas. Somewhere between 4 and 6 grams is a reasonably decent excess, and that's going to cover losses due to reaction with the acid and some powder inevitably finding its way through the bag while you make it. So let's see what happens. It works, but still 35 to 40 minutes. Doable for a lesson, but we want better, right? I had been reluctant to use a water bath for fear that it would make it difficult to see the nuances of the reaction, but responses from this community, this fantastic community, overwhelmingly pushed me over the line to return to the idea of heating up the solution. So here I am trialing for the first time in a water bath, but just below a simmer, somewhere between 80 and 90 Celsius, and the speed difference is worth the investment. We're well below 10 minutes now. The problem is that as you move past vanadium 3, brown. So what's going on here? There are a lot of other things in our mixture that the zinc is also capable of reducing, and we know that the colors that we're looking to see are highly pH dependent. This brown problem was noted by other people who'd suggested speeding up using a water bath, and it can be remedied quite easily by adding back some more acid at the end. We then get this nice purple color, but it's not exactly what we signed up for. Clearly, having a little bit of extra acid kicking around is not such a bad thing, especially if you're going to heat up the reaction. So I went back to the original recipe, and this time, instead of dissolving in sodium hydroxide, I dissolved directly in acid. You do need to be more patient this way. Crushing up little clumps of red powder with a stirring rod will help, but you definitely don't want to be trying to dissolve this in front of the class. It takes a few minutes. I used a 2 mol per decimeter cube solution of hydrochloric acid this time, both acids work. However, the chloride ion can't be reduced by the zinc, and the sulfate ion definitely can. So we're helping our reaction by removing a possible side reaction and starting off with a little bit more acid in the mix rather than losing some of those precious protons in the neutralization of the sodium hydroxide when we're making up the solution in the first place. It reaps some benefits. And now, my fellow humans, we have come to the end of the journey. If you skipped past all of the other stuff in between, I don't blame you. Just know that there are reasons for what we're about to do and the way that we're going to do it. I have a 1 litre borosilicate beaker ready with some water on a hot plate below somewhere around 80 Celsius. If I have just enough water to float the cell culture flask, that's one of these, away from the base, then I know that there's absolutely no risk of the polystyrene that this is made of, a melting point somewhere over 200 Celsius, that's not going to deform. If you don't have one of those flasks, a 250 ml conical flask works as well, but I do like those flat surfaces for good color clarity. In goes some 0.05 molar solution of ammonium metavanadate 5 dissolved in 100 cm cubed of 2 molar hydrochloric acid. You don't have to use the whole lot. Here I think I used about 30-40 ml. Don't forget the safety protocols from earlier when you're handling the toxic powder to produce your solution. Once the solution is made, eye protection is fine. I have some cotton wool on hand to place into the neck of the flask and reduce air coming in, but to be honest, I've never found this to be one of the major problems. And unless you're leaving solutions out for more than like a few minutes, you're probably going to be okay. Now I can lower in a tea bag, and I'm using one of the sort of string tag tea bags, and that's containing my zinc powder, as mentioned before, a couple of spatulas somewhere between 4 and 6 grams. Use a clamp to hold the tea bag close to the surface of the solution so that bubbles rise away from the color that you want to see below. The lower oxidation states also have higher density, so they will sink through the solution and mix nicely. Only now do I add water from a freshly boiled kettle to make a larger water bath in which the reacting solution is totally submerged. My thinking here is that the transition to vanadium 4 is actually quite quick, and if you'd preheated the solution, it probably would go a little bit too fast to see any nuance. By submerging in this way, the temperature of the solution is going to increase by the time that we get to the lower oxidation states when we need that kinetic boost the most. And there you have it. Vanadium 2 and well under 10 minutes. Removing the tea bag now needs to be done quite carefully. The more concentrated acid solution that we're using definitely weakens it a lot faster. So I tend to tilt the culture flask on its side, carefully pull the bag out with a washing up bowl underneath to catch anything that sort of breaks on the way out. Goes without saying that you should remove the bag as soon as you've convincingly reached vanadium 2. You can, of course, now re-oxidize with 10-vol hydrogen peroxide or 0.1 molar acidified potassium manganate 7. In the former case, you'll produce the pleasingly titled oxo-peroxo vanadium 5 ion. That sort of blood red color gives us a final flourish. Don't forget that your solution still contains vanadium, so CLEAPS members should consult Waste Protocol W7. Dilute and dispose down a foul water drain. If you don't have one of those in the prep room, then a toilet would also be suitable. Obviously, none of the above takes away from all of the fantastic opportunities that you have to explore other oxidizing and reducing agents to determine and practice feasibility of reactions. If anything, this actually allows you more time for those reactions rather than getting bogged down by this one dragging itself out over a longer period of time. There are, of course, myriad alternatives to play with. Angus Alchemist on Twitter suggested making a density column with the colors, which was really beautiful. I've seen people leave large columns to naturally develop over a number of days in a protected location that remains visible to passing students. And of course, Bob Worley had some other microscale ideas. I loved his notion of starting with 3 tubes, each containing zinc wire, and having left them in boiling water, simply removing the wire from the first tube to go blue, and then adding that wire to the other tubes, and then when a tube goes green, you remove the wire from that tube into the final tube, which now has 3 pieces of zinc in it, hopefully driving it down all the way to vanadium 2. I don't know how long this whole thing has taken me in total, but I'm hoping that that time will save you time and make for some more meaningful class discussions after a demo that does exactly what you wanted it to do in the time that you wanted to do it in. And if it doesn't quite do that, then hopefully you'll have picked up a few tips along the way for fixing the problem. Until next time, when I hope I have something a little bit simpler for you, take it easy. After all that, it's still blue. Use my technique.